My name is Li Ping Zhou from Peking University in China. And it's our great honor to have a distinguished speaker today, who is Dr. Pradim and Srivastava from India. Pradim is actually a member in the SSC of Pages, and he works in the Indian Institute of Technology and the Wadia Institute of Himalaya Geology, India. And Pradim was trained as a fluvial sedimentologist, geomorphologist, and a luminescence dating specialist. And he tries to understand the tectonic evolution and the river responses to climate change of different timescales in Quaternary. And so today he's going to tell us what he has learned about the flood history of the Himalaya, a geologist perspective. Now, Pradim.
Thank you, Professor Laping Chow. And it is definitely an honor to be part of the Pages OSM and to be able to give this plenary talk. And I now request the tech support to share my slides. Okay, should I do it at my end?
Yeah, you can do it from your side. Yes.
Okay. Are my slides visible, sir?
Yeah, looks fine. Yes.
Okay. Yeah. So thank you once again, and greetings to all the people, all scientists and students who are attending this session. And the thing which I am going to present is really represents my last 2-3 years of work with my students in Himalayas. And this is something which actually started in 2013 when India really got struck up with very large flood, and thousands of people were killed and billions of worth economy was lost. And that made me travel all across Indus, Brahmaputra and Ganga river systems of Himalaya with all the students. But then exploring the literature, I realized that globally, you see that most of the South Africa, Southern Asia, and some part of the South American continent is at the global, is at the real risk of floods. And the mortality is also concentrated in the southern part of the globe. Largely it's because of the higher concentration of the population, but also you can see that overall the largest disaster in terms of the losses is flooding globally. And this makes me feel that probably the branch line concept is still holding here in terms of when we see the global disasters like flood. And this probably is the reason why, these countries which are actually lying south of this branch line largely do not have data base that can serve the informed policies, right? Of course, large part of China has some data, some part of South Africa, and some very little part of South American rivers have been studied in terms of the flooding history. So here in this talk, I'm going to present some data what we have generated or what we have actually understood in this Himalaya. And you can see that Himalaya actually hosts few of the very large river systems like the Ganga, the Brahmaputra, the Yangtze, and the Indus. And these 4-5 river systems actually support somewhere around 1/5 part of the global population. And you see this formation of Himalaya, which one of my students made this movie. You can see it's a sandbox model that it is actually composed of several thrust sheets lying over one over the other. And as the Indian plate moves, this Himalaya actually keeps on achieving a particular kind of an orography. And this is how this profile of the Himalaya looks like. If you see the southern front of the Himalaya, which is at the exit of River Ganga, and as we go to Karakoram and southern part of the Tibet, this is how the geomorphic profiles looks like. It keeps on approaching, achieving a little elevation from Himalayan frontal thrust in the south, and as you move up, we have main boundary thrust, and then all of a sudden the gradient picks up at main central thrust, where the relief becomes really very large. And at the same time, if you see the rainfall profile over this geomorphic system, you can see the first rainfall high lies just above the main boundary thrust, which is the physiographic transition 1 in terms of geomorphology. And the second rainfall high lies just above the main central thrust, which is again the physiographic transition 2. Now let us see, this was how the headwaters of Ganga were looking like when we had a flood of 2013. Somewhere around 6,000 people died and 500 million worth of US dollars economy was lost. What we did, we started moving in large part of the Ganga basin, and we were trying to understand the damage elements like the landslides, the riverbank erosion, like the damages in bridges and culverts and roads. These are the things. And to give one example, you can see that these are the landslides. Alone in the Ganga Valley, we had around 700 plus landslides which were activated or reactivated. And these landslides, if you see, form a certain kind of a cluster. And this cluster basically is conforming to these two physiographic transitions. Physiographic transition 1 lies in this southern part of the catchment, and physiographic 2 lies just above this. So this, what we came to know, that probably there is an element of predictability in terms of damage when a flood of magnitude that we experienced in 2013 strikes to Himalaya. So this is one thing which we learned, but we know now that probably we can lay our hands on certain kinds of damage zones which can be predictable. But we do not know what is the recurrence interval of these floods, what are the magnitudes of these floods, and where do they erode, and what actually forces these floods. So to understand this, we started looking for flood archives. And these are one of the very simplest flood-driven proxy deposits. Like you can see that this is one sand and silt couplet. The sandier part is rippled, often bioturbated, sandy, parallel laminated sand. It is capped by a clay silt cap. And this one couplet represents one flood. And this sand part is normally deposited on the rising limb of the flood, and the clay part is deposited when you have a waning flood. So that is how you find certain kinds of sequences where you have a stack of flood deposits or a stack of these clay silt couplets lying over each other. You are actually seeing a flood history, and that is these kinds of the deposits we actually targeted. Okay. So now I'll give you a few examples from the two major river systems, like the Brahmaputra that drains towards east, and the Indus that drains towards the west. And this is the southern edge of the Tibet and beyond the northern front of the Himalaya. You see, this is the river profile, longitudinal river profile of Indus, and this is the longitudinal profile of the Brahmaputra or the Zanskar, right? So if you join, because these two river systems are overlapping to each other, it is all. We can see that if we join these two river profiles side by side, what we see actually the Tibetan part in the Indus lying somewhere around 5,000 plus meters, and whereas in the Brahmaputra part actually goes down to somewhere around 3,000 meters above sea level. And this part of the southeastern Tibet actually receives rainfall as high as 1 meters per annum, whereas this part of the Himalaya in Indus Basin receives rainfall of less than 100 millimeters per year. So there is an order of magnitude difference in the in the rainfall, and of course there is a difference in the continental scale geomorphology. This part lies 5,000 meters above the sea level, and this part is actually goes towards the equator because the Himalaya is forming an arch. It goes towards the equator, and also it has a lower elevation. Actually, Tibetan plateau is dipping towards the east, and this actually explains the magnitude of the floods that two river systems actually experience. These are the flood stacks in Indus in the right hand upper corner. You can see the flood deposits are of sub-centimeter, centimeter scales. Whereas in Brahmaputra, you can see the one short deposit is around 15 meters or so. So this explains the order of magnitude of the flood that these two river systems experience. And these differences is actually are being controlled by the continental scale geomorphology. And this is something what I was talking about, a geologist perspective in terms of understanding of flood origin and the flood magnitude in Himalaya, right? And in another story that goes along with these floods, and if you are fortunate enough, we find sometimes within these flood deposits, stacks of flood deposits, we find the human remains, not human remains exactly, but imprints of the humans. These are the baked layers that are the archaeological locales, and they are actually the huts where the people were sitting and cooking their food. And you can also find within these baked layers some chewed bones and some cow dung, dung cakes. I don't know what kind of dung cakes are these, and some unfinished stone tools and some finished stone tools. So what we did actually here, we went to the Zanskars, headwaters of Zanskars, the lower regions of Zanskar. Zanskar is the major tributary of the Indus. Indus flows just along the contact of this pink is Ladakh batholith or Trans-Himalayan batholith, and this is Indus molasses. And the Indus flows along the contact of these two tectonic units. And we wanted to know that what is the contribution of flood sediments of these Zanskar, which actually drains the southern part, molassic Himalaya. And we also wanted to know that what is the flood chronology of these deposits. So we studied somewhere around 15 lithologs, locations, and these locations, they actually look like sometimes like this. And this is the confluence of Zanskar River with Indus, and most of these slack water deposits, SWDs, are actually discovered or they are located at the junction of these two river systems, and that is understandable because the slackening of rising flood actually takes place inside the smaller tributary, where the flood energy goes down often to minimum. And these are the very typical locales of the where you can find these slack water deposits. And we counted the flood deposits, we sampled them for various reasons, and these are the luminescence chronology. And this is one of the huts which I was talking about, the baked layer. We have carbon-14 dates, and we found that 22 large floods. These, you see, we have a cross section at this place, and these flood deposits were lying somewhere around 11 to 20 meters above the modern riverbed, right? And using the chronology, we found that these floods were clustered between 13 to 9K. And this was somewhere around when the Indian summer monsoon is strengthened to its optimum after the last glacial maxima. And this suggests that Indian summer monsoon actually penetrated to drier part of the Himalaya in southern Tibet when the climatic optimum took place. And if you see the discharge calculation using various Manning's equations, we found that the discharges of the peak floods during the early Holocene climatic optimum were as high as 6 times of the modern floods, right? And we clubbed all the chronologies of these Zanskars and the Tibetan this Indus rivers. We found that probably we had in the early Holocene and old Holocene, we have 3 different clusters of floods. The phase 1 was somewhere around 14 to 12K. Phase 2 was in 10 to 8K, and phase 3 was 7 to 4K. And these were the when phases when the flood frequencies were higher. And the interesting part of this story is this, that these are the human herds, and the human presence was increasing when the flood frequencies were also higher. And it is only during the later part of the Holocene when we are finding most number of the herds. That means the human presence in Ladakh actually increased during the middle part or middle to late Holocene, when the flood frequencies were also higher. And these, you can see, this is the Pangongso data of how it all from the Chinese side. And this is basically a deuterium of leaf wax. And this leaf wax data suggests that just around 12K or so, this Indian summer monsoon contribution to Lake Pangongso was increased. And that is when the flood frequencies were also higher. And this indicates that floods in Indus, and at least in the upper catchment of the Indus, are controlled by the Indian summer monsoon. And that is when the inbound human migration probably also takes place. And another part, when we compared the flood histories with the East Asian monsoon dominated Himalaya, Yellow and Yangtze, and these rivers, many of these rivers, we find that these rivers actually were experiencing the high frequency floods when the Indus was actually depleting. So there is a seesaw kind of a relationship between the ISM or Indian summer monsoon and the East Asian summer monsoon. This actually, when you see the modern instrumental data, this remains the same. That's why our story is also suggesting that the modern relationship between the ISM and the East Asian summer monsoon actually may go back to Holocene, can be extendable to Holocene. So this was one part of the story. And another part of this story was the provenance of sediment. We find, we dated a lot of zircons separated, detrital zircons separated from the flood deposits. And we found that Zanskar is the major contributor in the flood flood sediments. Therefore, the hotspot of the erosion in Indus catchment, in the upper part of the Indus catchment, actually lies in the Zanskars, or lies in the higher Himalayan crystallines itself. And this is very important conclusion to be confirmed. The conclusion says that we all know that in the better part of the Himalaya, it is the higher Himalayan crystalline, the crystalline core of the Himalaya being eroded most, and this erosion is being driven by the strengthening of the summer monsoon. And what our finding is suggesting that this stands true for the dry part of the Himalaya as well. And when we go to the Brahmaputra, the eastern tributary, major tributary, that is Yangtze, Yarlung, Tsangpo, and this is the profile of the Tsangpo River, and this is the Tsangpo Gorge, and these are the places where we sampled. As soon as the river profile loses its gradient, we can see that most of the deposits, flood deposits, are now located. And when we dated them, these deposits, and tried to make their estimate their flood discharges, we found that around the middle Holocene, around 3K or little more than 4K floods, these floods were as high as the magnitude of 10 to the power 7 cumex. And this actually qualifies these floods in Brahmaputra or the Tsangpo to be called as the mega floods. And these are a few of the rarest floods that occur on the face of the earth. So Brahmaputra actually, because of its geomorphology and its interaction with the Indian summer monsoon, is vulnerable to the largest of the large floods in the Himalaya. And that is being explained by this work. And we did a lot of this isotopic fingerprinting, and of course the lithic fragments and all the petrology related to provenance fingerprinting. We found that the floods were actually originated on Tibetan Plateau, and these floods were originated on Tibetan Plateau due to the glow or the breaching of larger lakes that were glacial dam lakes or the moraine dam lakes, and these running water or gushing water exhumed a lot of material sediments from the crystalline core or the Zanskar gorge, and the material was finally deposited at the Himalayan front. And these floods were actually middle Holocene floods. When the Indus was depleting, these floods were of the mega flood category. And you can see that order of magnitude difference in the flood deposits. And that is now, to conclude, we found that large floods of 10 to the power 4 cumex in Ladakh occurred during the wetter phases of Holocene, actually Holocene climatic optimum, and that's when the human activity also increases there. And these floods are largely eroding the higher Himalayan crystalline core. The floods in northeastern Himalaya, that is Zanskar and Brahmaputra, during the Holocene were of the mega flood category, originated in Tibet and exhumed the deeper rocks in the northeastern syntaxis. Thus, now with all the modern flood deposits, modern flood data of 2013 and the paleo flood deposits, paleo flood records, we now know where are the damage zones that are likely to occur in Himalaya when we have the floods like 2013 and the larger floods. Therefore, the damage zones in the setting like Himalaya are predictable. And we also now know, better informed, that what is the water and sediment routing and erosion hotspots in Himalaya when these kinds of floods occur. So all we need is a better informed policies and the watchfulness. And my signing off message will be that global geoscience organizations like PAGES, INCOA, IUGS must contribute to Global South in terms of understanding these kinds of extremes. Thank you so much.
Thank you, Pradim. This is a very interesting talk. So now the floor is open for questions. Pradim, we have one question. Now we go straight for the questions, okay? And I don't know if you can read, but I can read out the question. The relationship between the flood and the human occupation is very interesting. Could it be possible that human occupation was there, but the floods have eroded the evidence for it?
This is, yes, of course, this is just a statistics of finding because you see the flood stacks are there and they preserve the story of the larger occurring floods. The smaller floods, they are not preserved there. The floods that are smaller there, smaller in magnitude. So larger and larger successive floods are preserved. And very interestingly, in one of the sections, we find that over the 1,000-year time scales span, we have 3 floods, 3 human herds. And this explains that the people were actually using these rivers, banks and floodplains continuously over the period of 1,000 years. And they were exploiting the geomorphology and river hydrology. So yes, you're right that some part of the story may not be there, but whatever we have, the statistically suggests that middle to late Holocene probably is the time when we have larger density of occurrences of these herds, and that's how I relate to human presence.
Thank you, Pratim. I actually have a more technical question. For this very fast deposited sediment, I would imagine that the bleaching will be an issue, and you seem to get a very good OSL dating there. Right. Is that, could you say a few words about that?
Yes, and it's a very, very understandable question that can be in anybody's mind. And the thing is I talked about the slack water deposits and slackening of the water sediments. These are the deposits that occur in suspension. These are the suspended load of the floods, and they are deposited at the shallowest part of the basin where the slackening occurs. And this is the reason we believe that these are the most bleached part of the flood deposits. And that is the reason we are actually able to get the good chronology out of these. Yes, in the northeastern part, we struggled to get the good chronology. And that is the reason that we could get only few ages. You can see that large number of older ages are also published by Americans in Oregon group. But we are now very sure that we have some ways to understand that whether the sediments are bleached or not. You can actually relate the ages or the paleo doses with the luminescence intensities, and that's what we did. And there are several other statistical treatments that is done to the data to actually get the best age out of it. So there is no last word in it. But again, as I said, that this is the best to the time actually.
Okay, thank you. Now another question is coming. So very nice talk. I'm just inquiring about the reason why we have an out of phase in flood frequency between the Eastern Asian monsoon and the Indian monsoon over the Holocene.
Actually, these are the two systems that draw moisture from two different pools. Indian summer monsoon largely comes from the Arabian Sea and the western part of the Indian Ocean, whereas this Eastern Asian monsoon draws large part of its moisture from the Pacific. And these are the two different pools, I believe, and these are the things which actually are operating at different time scales in terms of heating. And I may not be reaching out perfectly in this question, but I believe that the reason behind the two different pools supporting the two different moisture systems is the reason.
Okay, all right, thank you. Another question, great talk, thank you. I wonder why inbound human migration took place when Himalaya was drier. Was the environment suitable for human occupation when the climate was drier?
Actually, that is the take-home message. The large part of the drier Himalaya, when it starts experiencing the floods, it becomes the greener pastures. And these are the times when large number of wars occurred to annex Ladakh, Himalaya, historically going. And that is actually true that modern times it's a hostile kind of climate. But in the early part of the Holocene, when climatic optimum was there and flood frequencies were higher, I believe that these systems were much greener, and we have that data from the Pengongso from Chinese side, how at all, where the leaf wax data is suggesting that vegetation and their pollen data also that suggests that this Ladakh was greener. And we believe that aridity in this part of the Ladakh or southeast Tibet is very young. I mean, it is less than 2,000 years old. And Pengongso data suggests very nicely this. Because the salinity in Pengongso is as young as late Holocene.
So it is relatively drier,
yes.
compared to, okay, right. Very interesting, right. Okay, any more questions and in the audience, or you are still digesting what Pradim's told us? Okay, it looks time is up, and we now have to end this plenary session. And Pradim, thank you very much again for this very exciting.
It was very nice interacting with you, and it is my honor that you chaired the session, sir.
Right, and another thing I just want to say that this is very interesting, and we could find a way to share the publications that you mentioned with our audience. I think this is the way that having this online meeting and losing the opportunity to talk to you in person. So let's do that. And I'm sure the pages will have a way of getting this shared, or interested participants or in the audience. Please send Pradim email. I'm sure he will be happy to send you to share the publications. Thank you very much.
Thank you so much.
Thank you again, and thank you for the team to make this a successful session.
Thank support all the way, sir. And thank